We have seen that we can do phasor transform on basic circuit variables. Like, for example, if we got v of t and I told you the magnitude is v of m cosine of omega t plus theta of v, we have seen that the phasor transform for this is pretty straightforward. All you have to do is just tell me it's the magnitude, and the phase angle for that phasor is theta v. And what I want to do now is I want to see how does that phasor transform apply to the basic circuit elements, specifically the resistor, the inductor, and the capacitor. And what I can tell you ahead of time is the following, that these circuit elements are all linear circuit elements, and if you excite them or apply a sinusoid to them, they will respond with a sinusoid. Be that as may, with a different phase and magnitude maybe. So let me get to the details of each one of these elements separately. So I'll start off with the resistor. So we have seen in a time domain that a resistor has a voltage across it and a current flowing through it. And let's assume that the current flowing through it at this point is a sinusoid. And I'll tell you, well, it has a magnitude of I of m, and I decided basically that the phase, I'm going to call it theta of I, so that we know that this is related to the current. So before I move on with the idea, I just will perform phasor transform on this particular current, not the resistor, just the current, because we will need it later. So phasor transform tells you take the magnitude, you take the theta I, and that's it. That's the phasor transform for this particular current. All right, so going back to the time domain. So in the time domain, we know that Ohm's law tells me simply that V is I or R times I. Okay, let me just do that here, R times I. But it just happened to be that this time that V is a function of time and I is a function of time. So I'll substitute the value of I of t, which is just simply I of m cosine of omega t plus theta of I. Okay, and that's basically V of t. All right, so now what I will do is I'll do a phasor transform on this V. This here now, while we did the phasor transform on the current, let's do a phasor transform on the voltage. I know this. So from V of t to uppercase V, and that will equal, well, R and Im is the magnitude. So this one here is very similar to what we got. We got an I of m originally in the I, and now these two are a scalar because both of them are numbers. So this is the magnitude for this particular sinusoid. So what about its phase? Well, its phase is just simply theta of I. So that here is the voltage in the phasor transform. Okay, but wait a minute. Have we seen these here? We have. So let me just rewrite that. So V is just simply R times I. We're in the phasor transform. And as it turns out to be, that in the phasor transform or in phasor domain, R is simply R, and voltage is here across it, and this is basically the current. And as it turns out to be, that this here is Ohm's law in the phasor domain. So Ohm's law in the phasor domain, that means I still have to worry about passive sign convention, by the way. So let me just write that here in red. So it's the same exact thing. It's just when you convert the resistor into the phasor domain, everything stays the same. It's still R. And the phase for the voltage in here, if you take a look at it, is the same as the I. So there's no phase difference on R, does not introduce any phase difference. And if I'm to plot the phasor diagram for this particular one, what I'll get is the following. I'll get that theta of V and theta of R are the same, and the I and the V are basically both phasors. They're rotating the same, and they're in phase because they're actually exactly the same time. So if I'm plotting a couple of sinusoids, this is what I'll get. I'll get that both of them will reach the maximum at the same time, will reach the zero at the same time, and the minimum at the same time. That's what happens in here. V is a little bit higher than I because if you think about it, here actually in the phasor domain, V is just simply R times I, and R is a positive entity, so it's actually just increasing. V is just a little bit larger than I. So that's basically how we deal with resistors in phasor domain. We basically do nothing. We just basically treat R as R. All right, so let's move on to a more interesting thing, which is inductors in the phasor domain. So I'm going to do the same thing, okay? So I'm going to excite it with a current, okay? So here's what the inductor is. I'm going to basically excite, I'm saying excited, but I'll apply a current to it, and I'm going to assume that current is actually also a sinusoid. I'll do the phasor transform on the current that I'm actually applying to this inductor, and I can tell you that it's I of m times theta of I. Now, what do we know? I'm going back to the time domain, and what we know is the following, that V of t, which is the voltage across that inductor, is just simply L times d I of t divided by d of t. All right, so we know what I of t is because we have it in here, so let's take the derivative of that. So what we do is L times the derivative of this equation, which is just simply I of m times omega, and the cosine is simply negative sine and omega t plus theta of I, okay? And that's basically here is V of t. All right, so what I want to do right now is I want to convert, so we converted the current into the phasor domain. Let's convert the voltage. Now I have an equation for voltage that's converted to the phasor domain. Well, now this here is represented in sinusoid, and convention tells me, and actually it's negative sinusoid, so convention tells me that you have to move it to the cosine. So, and if you remember from that quick diagram in here, what we have is we have a cosine, and this is sine, and this is negative sine. What I'm trying to do is I'm trying to move from here to here, so all I have to do is just add a 90 degree. Okay, so what we will do is we will do the following. This is L times I of M omega cosine omega t plus theta I plus 90 degrees. Okay, that's basically V of t. Now we can perform phasor transform. So phasor transform tells me that V of t becomes V, while L and I of M and omega, they're all just numbers, so they stay the same. And I'll just basically write them as omega L I of M. I just rearrange them for a reason you'll see shortly. And this one here, the angle is theta I plus 90 degrees. Okay, so what we have in here? What we have in here is, if I rename this as V of M, so I'll get V of M, and this one here, I'm going to say that theta V. And what we get from here is the following. Theta V is just simply the original theta I plus 90 degrees. That's what we have from these two in here. Okay, so what I have done is, this is the original current in the phasor domain. I have converted the voltage into the phasor domain. It just happened to be that this here is the magnitude for the voltage, and the theta V is just happened to be 90 degrees ahead. So if I'm to plot these in the phasor diagram, this is what we get. If we have a current, well, V in here tells me it's the current plus 90 degrees. It's 90 degrees off. Okay, and as it turns out to be, the inductors, if you remember, they change, or they oppose the change in current, and as it turns out to be, when sinusoid, they make the current lag behind the voltage by 90 degrees. So the current now is lagging behind the voltage by 90 degrees, and because of that, so it opposes the change in current, and in terms of sinusoid, it makes the current lags behind the voltage by 90 degrees. And this is what you see in here. What you see is actually the voltage is reaching the maximum before the current because of the inductor. All right, so let me just continue here just to do a few things. So what I'll do is I'll do a little bit more algebra on the original one in here. V equals omega L I of M, okay, and this one here is theta I plus 90 degrees. I just rewrote them because I'll do a little bit of algebra, and the algebra I'll do is the following. So this is V omega L times I of M, and this is technically theta I times times the angle, which is 90 degrees. Because remember, this is e to the j of theta I plus 90 degrees, so I can just write it j theta I and e j 90 degrees. That's basically what I've done in here. Well, speaking of that, ej of 90 degrees, okay, so let me just write it in here in different colors. So this one here is just simply e to the j of 90 degrees, which is, if I'm write it using Euler's equation, this is cosine of 90 degrees, which is 0, plus j of sine of 90 degrees. So this is just simply j, just because this is 0 and this is 1, so what we end up with is just j. So let me just rewrite this one here. What you get is v is just simply j omega L I of M, and this is theta I. But we have seen that I in the phasor domain is here now. So we can just rewrite this here as V is just simply j omega L times I. And that's how the inductor acts in the phasor domain. So in the phasor domain, what we have an inductor in here. Okay, so the inductor has a current and has a voltage across it. Okay, and this one here is the inductor, and we don't deal with it as an inductor this way. What we say is this is j omega L, and we deal with it as if it's a resistor. We don't call it a resistor, we call it an impedance, by the way. And of course, because of that, we can basically apply passive sign convention as well. So just a very quick note, what we have started with is the following. We have started with some sort of a derivative, okay, and we ended up with voltage that there's no derivative in the phasor domain. So in the time domain, we had to take the derivative of the current. In the phasor domain, we just had to multiply it by some sort of a complex number. We just got into complex numbers. And this is very characteristic of a lot of transformations in engineering. So you run away from the math. So instead of doing derivative in the time domain, you go to a different domain and you end up with just simple algebra. Well, complex algebra, because we're using complex numbers. Okay, so moving on, now we go to the capacitors in the phasor domain. Same type of analysis, same like anything else. So what we have in here, and now we're doing it just for simplicity. I have a capacitor in here. I'm going to excite it, or I'm going to apply voltage across it, and I'll find the current. It's just because it's simpler this way. Either way, you can excite it with the current, it will give you a voltage that is also a sinusoid. But anyway, we'll do a phasor transform on this. What we'll end up with is this is V, the magnitude is V of M, and the phase is just theta V. Okay, and what we know in the time domain is V of t is simply, actually what we're looking for is I of t actually. Let me just do that. What we're looking for is I of t, and we know is just simply C times dV of t divided by d of t. Okay, so we're going to do that here, C, well, I'm going to take the derivative of that. The derivative of this is just simply V of M omega, and this cosine becomes minus sine of omega t plus theta V, okay? And now, of course, I'm going to convert it to phasor domain. And in phasor domain, what I have is the following. I'm getting from negative sine all the way to cosine. I need to convert this sine, and this is negative to cosine, in order for me to do phasor transformation. So what I'll end up with is the following. I'll get omega c v of m cosine omega t plus theta v plus 90 degrees. Okay, and again, this is basically here's I of t. So I'll do now the phasor transform. So the phasor transform tells me that this is I, and this one here is omega c v of m, and this one here is the angle, which is theta v plus 90 degrees. Of course, we can just say that this here is I of m, and this one here, we can rewrite it as I of m times the phase angle, which is theta I. And of course, if you compare these two, what you'll end up with is theta I equals theta v plus 90 degrees. All right, so remember the capacitor opposes change in voltage. So as it turns out to be, if I'm to plot this here in phasor diagram, what I'll end up with is the following. So the capacitor current leads the voltage by 90 degrees. That's what we have in here. So if you take a look in here, you will see that basically the current reaches maximum before the voltage because it's leading it by 90 degrees. So an inductor opposes the change in current in the time domain. In the phasor domain, it lets the current lag behind the voltage. Capacitor, on the other side, it opposes the change in voltage in the time domain. So what it does in the phasor domain, it lets the phasor or the voltage lags behind the current by 90 degrees, or it lets the current leads the voltage by 90 degrees. All right, so we're going back in here, and I'll rewrite this one here. So what we have is I of m. I'm just going to rewrite this one in here is omega c v of m, and this is theta v, and this one here is 90 degrees, which we can represent it with a j. So what we get is I is just simply j omega c v of m theta v. But we have seen that this one here, okay, is just simply v in the phasor domain. So I'm just going to rewrite this. So what I end up with is j omega c, and this is v. That means if I'm writing v, I'll get 1 over j omega c, and that one here is I. So the capacitor in the phasor domain, you will have a voltage across it, you'll have a current flowing through it, and you can deal with it instead of c as 1 divided by j omega c. And I've also seen people using it negative j times 1 divided by omega c. They're the same because 1 over j is negative j. Okay, so we can say basically the same thing. We started by a derivative in the time domain, and we ended up with just simple multiplication in the phasor domain. As before, phasor, well, now what we have to do is we have to do plus minus in here, and the reason why is because passive sign convention still applies in here. So to summarize all the relationship that we've seen for all three circuit elements is the following. So an element, which is R in the time domain, you basically deal with it as R. In the phasor domain, it stays as R. Okay, the voltage gets voltage, the current gets current, but then R stays as R. The inductor, what we have is the voltage goes to voltage, current, actually the derivative of the current, well, we just deal with it as a current, but instead of dealing with L, what we do is we multiply J omega L. Okay, and the capacitor is, this is the voltage, this is the current. What we have is we have j omega c as the impedance.